and I'd now like to hand back over to Alan Smith for the DC Data Center Sustainability track. Thank you very much, everyone.
Richard, you can come on up. So we are kicking off the sustainability part of the program. I'd like to thank Alan for stepping in and facilitating the AI HPC track that we had today. The track was curated by Julita's colleague at the Barcelona Supercomputing Center, John Davis, and you can see from the quality of the program, he did a very good job curating the topics.
Absolutely.
Yeah, thank you, Alan. So as we welcome Rich to the stage, Rich Kenny, he is the Managing Director of Interact, Research and Sustainability Director of TechBuyer. He's a visiting research fellow at the London South Bank University School of Engineering and a nice guy to boot. So his talk is Hot IT, a False Economy, Impact of Temperature and Location on Efficiency.
Nice one. Thanks, Alan.
Cheers.
Can everyone hear me okay? Yeah, good afternoon. Okay. Thanks for that introduction. I appreciate it. It makes everything easier. So what we're going to be talking about today is a three-step approach to proper DC creation, management, and optimization. So we've just published in the IEEE Journal of Sustainable Computing around this topic, hot IT, and whether or not increasing temperature set points in data centers is a false economy. So I don't know if you're aware of this at the moment, but Equinix is looking at making a default 27-degree shift. That's the top of what we would class as an ASHRAE allowable envelope. The idea was that it will save carbon, it will save energy. That's not necessarily true, and so I'm going to break down why that might not be true. We're going to shift the paradigm on how you build data centers here by looking at, rather than saying how do we optimize the building and focus on metrics around the building, such as PUE and other metrics as part of the EU Code of Conduct, we're going to look at where we should probably start. And we should probably start at the location, then move to the hardware, then move to the actual cooling, then move to the data center itself. And that is completely opposite to how data centers are generally built now. The reason behind that is because location is a key aspect of creating data center, and it determines what the impact of your temperature set points should be, what IT tolerances exist within that. So what I've got on this slide at the moment here is the current research that's been done into temperature's impact. And what we're going to look at is the temperature impact on IT hardware first. So there's been tons of really great work done by Google. There's been a load of great work done by Facebook, and it was while it was Facebook, not while it's Meta. And there's a bit of work been done by ASHRAE as well. The problem is most of the literature reviews on this are a decade old. So Intel did some great stuff that finished in 2021. Every single one of these, including Google, have looked at failure rates of hardware and the impact of temperature on failure rates, not on efficiency. So what they've done is say, if you run your IT hotter, does it fail faster? Does it fail more often? And that interplay between technology and temperature is crucial for understanding location-based metrics. What they found was there was basically no impact on failure rates as you raise temperatures, both to top end of ASHRAE allowable at 27 degrees and up to 30 and 33 degrees as well. There was no increased failure rates. There was no lack of redundancy caused by that. What I'm interested in is how does it impact the actual IT? Not does it break more often, but does it make it worse at doing its job? So this is what we looked at. We actually did 144 different configurations. That's the interplay between RAM, CPU, and storage, along with model. We covered every major model from between 2012 and 2017. We looked intergenerationally with the CPUs, looking at every generational CPU from an E5 V1 up to a V4, and then also the Intel Scalable first generation. So that gives us 7.5 years worth of CPUs. The CPU is the key driver in energy efficiency, and it's the one that has the most impact when it comes to temperature. So what we've also looked at then is to basically to air cool or not to air cool. Do you go with air cooling from direct air expansion, which is fundamentally basic refrigeration systems, air conditioning? The other option is what we call WC or water chill. This is where you've got a glycol and water mix to pre-cool air as it comes into the data center. We did not look at direct chip cooling. We did not look at liquid cooling because that's not what's going on in the market right now. That might be applicable for high performance compute. It might be applicable for AI. I have to tell you, that is less than 1% of the market in data centers. HPC is not the real world. HPC is a very unique use case, very, very important, very, very good, but it's not the real world. So I deal in the real world. I'm not a HPC specialist, I'm a hardware specialist. So we actually created, using the Green Grids tool and then rewriting the Green Grids tool to make it a little bit better, a case study based on Airedale's LDX D3. DC3 Centre, which is a data centre in London. What we're able to do is move the hardware analysis that I'll go through quickly to give you some context into a physical building that we could transfer across the globe and look at what happens when you take a series of variables, which is hardware and cooling, and place those identical metrics somewhere else in the world and see what the outside humidity and ambient temperature does to your data center. The reason we did this is because the majority of data centers are Frankfurt, London, America, Amsterdam. The majority of developing data centers are Africa, Southeast Asia, Latin America. This is where the next stage in data center construction needs to be focused. And unfortunately, everything we know about data centers doesn't apply to those regions in the same way. And no one's done any research on this, so that's what we do. So to start with, we need to look at the hardware, because we need to isolate single variables in research, right? You need to understand what the change in one leads to the change in another. So we need to understand what the temperature impact is on hardware to start with. So what we have is a custom-built wind tunnel. Professor Summers will know a little bit about this. He has one of his own, I believe, at Rise. This allows you to put any sort of U size in, any sort of width. This accommodates OCP equipment or standard enterprise equipment, and it allows you to move certain metrics around. So you can change the temperature anywhere between 15 and 35 degrees. You can change it from pressurized and non-pressurized to look at the impact on pressurization. It allows you to then benchmark properly. So most of your major manufacturers will benchmark on what's called a bench test. They'll sit a server somewhere and accept the fact that it might benchmark at 21 today and 26 tomorrow. What they don't do is control all the variables, pressure, ambient temperature, humidity, harmonization, and look at just what the change in configuration does. And this is crucial. So the next stage is, what does temperature do? This is what temperature does to efficiency. So on the bar chart, what you'll see is the blue is the low temperatures, 20 to 23, the orange is the mid temperature of 23 to 26, and the green is the top temperature, 26 to 30. The bar chart is the efficiency of the IT when you move just the temperature. Nothing else changes, just the temperature. What you see is a decrease in energy efficiency across every single generation of hardware, and they're more or less impacted, and I'll go into that in a minute. The violin graph, which I always think is a really cool graph, is the performance at every level of utilization. What that tells you is performance does not change with temperature. Efficiency does, performance does not. You run something hotter, it does not become less efficient, it does not become less capable. It does, however, become less efficient at carrying out work, and that is crucial. So we now know that raising temperature has no impact on the longevity of the hardware, nor on the performance of the hardware, but it directly impacts the efficiency. So it directly impacts how much carbon you use to generate operations and how much energy you use. So from a sustainability point of view, we need to be focusing on how do we maximize configuration level efficiency in data centers. This is when we look at other factors coming into play. So finishing off on the hardware piece, pressure and temperature has the biggest impact at extremes of utilization. So 0% or idle, 100% maximum utilization. In between the middle, you've got different variations. This is now also where generation of hardware is crucial. So that blue line that is massive up and down everywhere, that's the older hardware. That's the 2012 hardware. That's an R620. I've done analysis through Interact on over 350 data centers in the last 18 months. I have yet to see a data center that doesn't have kit older than 2014 in it. And that includes major national banks, that includes research organizations. Everybody has old kit, and nobody treats it the same way they treat the new kit, which is that it has a completely different appetite for temperature. You're telling me these things are unreliable as they get older? Well, someone's been running them for 15 to 20 years and they're doing just fine. But what we do need to understand is if you're going to run them, how do you run them in the most effective way possible? What's really interesting here, and this is something that we didn't expect to find, there's an R640 Silver, so that's a 2017 server, Silver being the first generation scalable. It has the lowest performance of pretty much all the servers, but it is the most temperature tolerant. It's an A3 rated server. We rarely see these. That A3 rated server has no impact on performance or efficiency up to 40 degrees. That is massive, because if we can make all our future CPUs and models that temperature tolerant as we get from this mid-range 2017 CPU, we can actually play a very different game in emerging data center technologies. So this is what happens to the CPU when you increase the temperature. Basically nothing in regards to its operating temperature. I don't know if you know this, but most CPUs don't run at 28 or 29 degrees. They run at 145, 235 degrees. So when you change the inlet temperature coming into a server from 26 to 27 degrees, the CPU does not care because it's used to 245 degrees. It's very capable of dissipating heat. Historical sort of knowledge on this has been that as you increase the temperature, you increase the fan speed. And that's true. So as you increase the temperature, the system has to cool faster, has to work harder. Kubik's law says that the size of the fan means as you accelerate it, it becomes harder to keep accelerating it. It uses more energy. So what we see is, across the board, when you raise that upper limit of temperature to, say, 28 degrees, you're seeing a 2 to 6% decrease in energy efficiency. But only 2 to 3% of that is caused by fan increased rotation. The other 3% at a base level is leakage current generally. And John will probably back me up on this one tomorrow, perhaps. But fundamentally, running IT hotter isn't just about it being harder to cool. There is a direct onboard impact from running systems hotter, and that is through leakage current. That's the interplay between the CPU and the system board. What you're seeing here on, by the way, the blue, and I know there's a lot of graphs on this. I like data visualization, so I apologize for the pictures. But what we're looking at here is the impact on fans. What we're seeing is there's very little impact on CPU temperature raising, quite a lot on fans. So what we've done is we identify what the IT does now. So first part of the puzzle, identify what temperature does to IT, cross-generationally, on a configuration level. Now let's look at what actually happens from a cooling point of view. When you raise the temperature from 21 degrees to 28 degrees, this is what you see. The green line is a water-chilled system. So this is the one I was talking about using pre-cooled air coming in, basically pre-cooled chilled air. And what you're seeing is in every single case, raising the temperature massively decreases the amount of energy required to cool that center. So when you take this data center in London and you make sure it's liquid, it's cooled with what we call water-cooled, so WC system, it always makes sense, irrespective of the IT, to raise the temperature. Always. Doesn't make sense for most of the direct cooling environments. Most of the direct cooling, where you're bringing air from outside, raising the temperature, the actual benefit you get from saving energy and raising the cooling is offset generally by the increased IT load and the cooling impact from the delta T. So your direct cooling, your air cooling system in London does not respond well to a raised temperature. It's basically a zero-sum game. So when you talk to the Equinixes of the world and they say, we're going to raise temperature, my first question is, where you're located, what hardware you've got, and what's your cooling system? So don't tell everybody that we all play the same game, we're moving to 27 degrees. We are not doing that. You need to know why you're doing it first. And now this is the interesting part on location. This is the ASHRAE map. We kind of recreated this. You won't have seen this before. This is probably the most useful thing I've done in my life, to be honest. And what it looks at is temperature and humidity across the globe, and it breaks it into what we call envelopes. So the 0, the number, corresponds to the temperature. So 0 being max temperature, 8 being coldest temperature. The humidity is your A, B, and C. So 0A is really dry, really hot. Not a massive surprise, it's pretty much sub-Saharan Africa. Look where most of our data centers are built. Amsterdam, Frankfurt, Sweden, London, New York. What color is that? It's all blue and green, right? So everyone's building data centers as if the whole world is blue and green, but it's not, because most of our emerging data centers are going to be built in Australasia, the APAC region, Latin America, Africa. They have very, very, very different impacts in regards to humidity. This is my favorite chart I've ever made, because this is a direct comparison between direct cooling and liquid, well, not liquid, and pre-chilled cooling. This is the impact of location on data center and why it cannot be ignored. At the top, we're ranging from the warmest, which is Abu Dhabi, right the way down to what we class as a 4A in Seoul. And it goes lower, it goes down to 8, and we've got Iceland, and we've got areas of Denmark within that. In the orange, what you're seeing is the impact on raising temperature for direct air systems. And for every single data center, it makes sense to range temperature for direct. But as the temperature's higher, Abu Dhabi, Caracas, Caribou, Jakarta, the percentage benefit you get is massive compared to the benefit you get when you're in a cooler climate, the traditional climates. Now look at water cooling. That's the section next to it. You actually become less energy efficient in those warmer regions by raising temperature. So in Abu Dhabi, you get a 20 to 30% improvement in energy efficiency by raising temperature from 21 to 28 degrees. You do the same thing with a water-cooled system. You go from 18 to 18.75. You actually use more energy raising the temperature on that water-cooled system in that region than just leaving it alone or running it at 21. And that runs to almost all the 2A and 2B regions. So most of the place where we're about to start developing, the majority of our data centers do not respond well from an energy and carbon point of view to raising temperature in a water-cooled system. What's worth noticing here, by the way, is that water-cooled systems are always more effective than direct air, regardless of where you are in the world. It's a better system, but there is a capital investment in that. But That being said, if you are in one of these developing regions with a water-cooled system, you do not want to be running 28 degrees. It does not have an environmental impact that benefits. This is the best way to show this. That is that series of tables as a graph. And what you can see is, on the bottom of the axis, you've got the zone. So 0B, 0A being the hot and arid regions. As you move towards 4, you get more towards London. What you're seeing there is that direct cooling has huge benefit in the warm regions, and it then starts massively tapering off as you get cooler. The inverse happens in the water-cooled environments, where it starts with a negative impact by increasing temperature and becomes very, very beneficial in, what would you know, 4A. That's what London is. So all of our knowledge around data center build, all of our knowledge around how hardware reacts, is all different depending on location. So we have to look at where this has been built first before we make a decision on the inlet, before we make a decision on the hardware. We have to look at data centers as a system of systems if we want an environmental approach to proper management of data centers. You change one variable, it changes something else. If the IT is older, it's less tolerant. If the IT is new, it's more tolerant. If it's a warmer outside climate, you've got a better chance of having a positive impact if you're a water-cooled system. But you must see where you are on that map. That's crucial. So key takeaway on this before we move to the Q&A piece. Fans aren't entirely responsible for the hardware piece as leakage current. Differential pressure offsets some of the impact, but not all of it. And basically, compute below 30 degrees, or in my view, below 35 to 40 degrees, completely unaffected, as is failure rates. So raising temperature could be an incredibly good environmental initiative. Could be. The other factors that we need to look at for DC is not just what's our PUE, what hardware are you running, what's the utilization rate, how are you cooling it, where is it being built. If we don't look at these 4 things, we will never build an optimal data center. That's kind of the most important thing. So what we always say is this stuff isn't simple. You know, when someone says something flat like we're doing this, you say you're doing this in this situation. You may not be doing it in another situation. And it's key to look at the context and look at the impacts. And this is the real world. So when we have these conversations about AI and we talk about direct chip cooling, that's wicked. It's really, really important. But it's not the real world. It's not where 99% of compute has been managed. It's not how most people are running systems. And so it needs a different way of thinking. Thank you very much. We'll do a Q&A now, if that's okay. And I'll be at the demo table later on talking about benchmarking. John's not allowed a question.
Hi, very interesting talk. I'd like to maybe just 2 questions. Well, one just to challenge you a little bit on the water cooling. It's quite amazing now we are seeing water-cooled servers really become into the market pretty quickly, including Supermicro providing water-cooled solutions. So I think you may find that there could be quite a transition to direct water cooling over the coming years, especially with the likes of ChatGPT type demands. My question is tilted towards the water side of things. I'm not sure I fully followed the arguments on the water versus... So I've heard that for energy recovery, we would like water-cooled systems to give you 65 degrees C or thereabouts output. So are you saying that this analysis plays towards raising the inlet water temperature so your outlet can get up to 65 C or not? Or is that a bad thing?
The key is not to confuse direct chip or liquid cooling with what we call chiller-based cooling or WEC cooling. So the examples we're using here are air-based cooling and chiller-based cooling. None of that is liquid cooling. Okay. To get proper heat management at the right temperatures and get decent, I'm not going to use the word waste because it's not waste heat, it's an opportunistic heat. To get that requires liquid cooling, and that's a very different conversation. That isn't what we're looking at, because I agree liquid cooling is becoming more mainstream, but from my experience of hundreds and hundreds of data centers, the average utilization is like 25%. There is no need for direct chip cooling for most of these enterprises, except at their really high compute levels where there is an absolute need for it. Right. So when we're talking high compute, when we're talking AI and ML, liquid and direct chip cooling is a vital technology to make those run better. For the rest of the world, they're probably going to stick with WC cooling, I think.
Thanks for
Does that make sense?
Yep. Yeah, thanks for clarification.
Thank you.
Next, yeah.
I'm going to have a notebook for this because John asked me a difficult question.
I'd like to start with the HPC thing first. So HPC guys will look at the hardware and look at the BIOS settings before they deploy it.
Yep.
Data center operators don't, or a lot of them don't. And so you get a lot of servers in data centers that are in performance mode or something like that. and they're not running at their best performance, are they? And you know that from the BIOS settings, from what you did. The other thing is that when people go to spec power to look at these results of performance per watt, the temperatures are not always uniform. So that depends on the manufacturer that's done the spec power analysis. It can be at different temperatures, so that actually influences those results. So I guess the question I have for you really is, wouldn't it be better? And this is the thing about liquid cooling, is that chilled water loops are great, but I think if we can get closer to the temperature of the microprocessor all the way out of the building, then we're in a much better place. And unfortunately, you can't get better performance with liquid cooling. It's the same as air cooling. We've done the tests on this. It's the same performance at the end of the day. The watt that goes into the microprocessor still does the same amount of work, depending on the temperature of operation, of course, as you pointed out. But we need to get, that's that train of heat recovery from the chip. That's the really tricky one to do. And you're right, there's not enough motion on this yet, but Moore's law is challenged. So the next thing we do, and I noticed that Angie had on her presentation, it was talking about Lowndes limit, she had dark silicon, but she never mentioned what dark silicon was. I don't think most of us understand what dark silicon is, but today most microprocessors only have 20% of their transistors alight at any one point in time.
Yep.
If we take the lid off that and light all 100% of the transistors, we are going to be drawing a lot more power.
Yep.
And it's going to be more challenging to get rid of the heat.
Yeah, and like I said, the key is then to repurpose the heat and redistribute it. And Deborah and I were talking about this earlier on today about the carbon impact of district heating systems and distributing that opportunistic heat. Because if the impact of digging up the road and repurposing the system doesn't outweigh the impact of the heat transfer, then it's the wrong way to approach it. The right technology and the right solution at the wrong place at the wrong time. And that's very much the point of this, is understand the place and time, understand the technologies, and then move forward.
Do you have a camera? You want my camera?
Next one.
Wonderful. Any questions?
cool.
Yeah, please.
Oh.
Can you repeat the questions?
Yeah, so that was about using different technologies for chips, and specifically aeronautical chips, right? And that sort of technology to reduce the actual requirements to cool. And that's I think that's another step forward that we need to talk about, is core density and extra frequency on chips, and how much is necessary and how much is fine. And that's very much John's point, is that you've got a lot of these existing technologies like AMD chips that have high core density through chiplets as opposed to monolithic chips. And the heat they can generate is monstrous. Like it's 245 degree TDPs. The ones you've got in the space system have much lower tolerance. But realistically, it's about applying the right chip to the application. Because no matter how good the technology you're applying, if you're not using it at a higher level, it doesn't have that benefit. Whereas for high compute, something like that could be really interesting. For really high compute usage, for really high utilization, which does push those temperatures up, something like that technology is incredibly useful for the knock-on impacts. But it's a very small use case. Cool.
Okay. Yes, please, Jens.
Do we have time for all this? I don't want to be eating space.
Yeah, 1310. This one, right? Yeah.
Cool, thank you. That would be rude.
So, yeah, so you were mentioning that the CPU temperature is not too much influenced by the air cooling.
Yeah.
So that was mentioned earlier that that if you do heat recovery and then you go to high temperature level direct cooling, right? You have a lot of advantages there. You can even go do free cooling at very high climates, right? So then this metrics would change. What we see in the roadmap of the chip manufacturers, the big ones, that they set with higher energy density, they lower the temperature, the maximum T-case temperature,
Yeah.
and then they say, okay, then you use direct liquid cooling, and then we are fine. Which has certainly an impact on the air cooling those systems, right? Then you need even more air going through. That means more fan power, more energy inefficiency. So what's your take on this? And also, your research is absolutely great, but how does it reflect kind of the change on servers, meaning going to lower temperatures? And would your recommendation be the same looking at the future servers, not looking at the ones that are placed right now in the data centers?
The future servers are way more heat tolerant, absolutely. That example with the silver we talked about, there's a 2017 one that's 40-degree tolerant. The future AMD chips and Intel chips, like the third generation scalables, they'll do 40 degrees, 45 degrees all day. ASHRAE has an envelope where it ranges it from A1 to A4, and that's the first a proper A3 I've seen. So there is still room for an A4 to have a 45-degree allowable, which is, you basically don't even need to cool that, you can just let it run. I think the key is to choose the right process of the right application, the right understanding of what we're doing, because no matter how efficient a chip is or how effective your cooling is, if it's unnecessary, it's unnecessary. So the key for me is to look at metrics like ITEU, which is the utilization of compute, to understand how we cool based on utilization. Because from that research, the key is at low utilization, it's quite inefficient, and at high utilization, it kicks out loads of heat. The majority is clustered around doing nothing and doing 25% with spikes up to 100. That's generally what we see in enterprise workloads. So I think the key is creating lower TDP chips at idle, where servers are spending a lot of their time. So exactly what you're talking about, chip manufacturers moving to much better high-use chip heat that can be repurposed, but a much lower idle chip heat, so cooling is much less required day to day.
Okay, may I just quick question to that? If your observation is that most of the data centers are only utilized by 10 to 25%, that's a huge impact on the environment, right?
Massive.
We have cloud computing, right? So wouldn't it be something we have to work on this first to get those servers utilized closer to 80% or something to get
100%.
Okay.
100%. The key thing, the point John was making as well, I don't know if you picked up on this, but between 2012 and 2017, there's BIOS modes set on servers where they default to performance, and they use twice as much energy at idle as they do versus a balanced configuration, but they provide zero extra performance, sub 90% utilization. So if you've got a data center at 25% running in performance mode, you can literally reduce your energy by 30% by flicking the BIOS, and it has zero impact. And I've done this with about 50 data centers in the last year, and all of them have seen decreases in energy of between 18 and 50% with no loss in performance, just by changing inbuilt BIOS modes from performance to balanced. So exactly what you're talking about. What needs to be looked at is how do we get the most utilization? How do we optimize low energy idle? And then what do we do at the top end? Because far too much time is focused around how do we cool, how do we move, how do we shift heat, whereas why don't we focus on low energy compute first? And that's very, very attainable. Good questions, thank you.
Yeah. I'd like to close with one last question. John, I've worked in dark silicon, so I can chat with you after if you'd like. I've done some investigations into it. In your talk, you kind of start to talk about a paradigm shift that can come from this work, but you don't explicitly say what that is. So we leave you in charge for the day. What's the paradigm shift you would call for in our industry around location, temperature, humidity, this analysis?
Yeah, I mean, sorry, I kind of said in kind of flip what we do. Rather than go building, fill it full of hardware with some cooling and stick it, I would completely change it to identify location, identify the tolerance of the hardware for that location, cool appropriately, and then think about the building, the facility, and everything else. So the paradigm shift is literally inverting how we currently look at data center design. Exactly that. Go, where's it going? What's going in it? How are we using it? Then how do we cool it? Then build it, rather than build it, fill it, hope for the best.
And that paradigm shift could enable this development in these developing nations, rapid expansion of data centers. That's
100%, because I think what we will see is in developing nations, they will be using older equipment, refurbished and second-hand, second-user equipment way more often than we'll see them using brand new, just based on availability and budgets.
Wonderful. Can we thank Rich for the wonderful talk?